Hello everyone and welcome to the Audio Foundry. I'm Lanson. Today I'd like to show you a program called WinISD. This is a program designed to help you design enclosures for your speakers. You can build sealed enclosures, ported, 4th order bandpass, 6th order bandpass, and you can also build some variations of this like with a passive radiator for instance. There are limitations to WinISD, but for a free program, it's pretty good. Once you get the basics of how to put in a speaker in WinISD's database, it's pretty easy to use. So I thought I would show you my minimalistic way of doing this that has been most successful to me using this program. To start off, you'll want to find a speaker that has teal small parameters that are complete at least to have the basics. And I will show you which ones are most critical here for an accurate calculation. WinISD will start factoring its own calculations in between some of these numbers. So we're going to load WinISD and I'm going to have it here partial screen, and I'm going to have the teal small parameters from a speaker I want to model. I'm going to use the CSS Audio SDX12, and there are teal small parameters here, and I'm going to take these and get these in a notepad just so I can reference them quickly. I'm going to have WinISD open, and I'm going to open up this create new project, and then I'm going to hit add new to start building a new speaker. So this is a CSS Audio SDX12. In the comment box, you can take details like the highlights here or whatever else you want to type and just drop it in. We're going to start here at the top at the QES, and you're just going to match this here, and then you're going to tab to QMS, tab past QTS and let it auto-calculate. And so this is a calculated value that is not quite exactly what the CSS Audio people put into their teal small parameters. But when it comes to WinISD, there are some fields you want it to calculate, and the difference should be negligible, not noticeable to your model. But if you do type in all of these numbers exactly, WinISD can get a little bit confused or start throwing errors that may not be real errors, and that's just because the calculation differences. So what I'm going to do here is continue on, tab through. If you're not sure, you can always wipe something out and hit tab and see if it auto-calculates. Next up, we're going to go here into FS and type in that and then the VOS. Now, the VOS will give me a chance to show you a WinISD feature here. I'm going to click where it has this L for liters, and you can see it goes to inches cubed, feet cubed, so cubic feet, cubic inches, and so on. This allows you to adjust your unit of measure. Now the unit of measure can vary in a teal small parameter listing. Just match them up. So this feature is inside WinISD for all of these that have an applicable switch in the unit of measure. Another nice thing is you can enter, say in this one, our VOS is 67.5, and so you might want to know what that is in cubic inches or cubic feet, and you simply give it a click and it will show you that number calculated. Very helpful. Tab past and get to MMS and type that in. Tab past CMS and RMS and RE, get to BL and type that in. Tab past DD, enter an LE if available, voice coil inductance. Tab past SD, which should be pre-filled and should almost match these numbers here. Next up, frequency for LE is not always published in parameters, but if it's not listed, consider 1000 Hz to be the number. What that would mean is that the voice coil inductance at 1000 Hz equals the 1.38 millihenries, and for at least a subwoofer, this is usually accurate. If it's for a mid-range or mid-woofer, the LE is usually factored at 10,000 Hz, but the parameters should specify if it's not 1000. Xmax, this is not the same thing as mechanical limits. This is linear travel. Xlim would be your mechanical limit if available. Next up, we'll pick the power handling, and this is not always inside the parameters here, but it usually is in the actual specs for the speaker. You would use the RMS rating. Okay, then tab through and save. Just verify that you've got the file name the way you want, put it in the drivers, save. Okay, so we are going to create a new project and we're going to add our driver we created. And we're going to select one driver and its placement will be normal. We'll choose a closed box and we'll just select this alignment, but this will be changed by us manually with enclosure size changes. We're going to label this project. I'm going to create another one exactly the same, and the reason is so I have a comparison on screen to aid in understanding the changes we're going to make, the pros and cons of your choices. So we're doing exactly the same thing. Now I've loaded 2 projects. They're not on the graph yet, and that's because I've got the graph currently set to SPL and the base is at 1 watt. So I'm going to adjust both of these to the maximum wattage for the subwoofer. The next thing I'm going to do, I'm going to take each of these and adjust the filters that I need to add. The first filter we'll add is a high pass. The high pass will be everything that passes past this number and up is considered high pass, and this is often to match your digital signal processor. I build systems with digital signal processing in mind. Most systems will have a 20 to 20,000 hertz frequency response, and so we add this filter not only to match what the DSP can do, and I'm going to add it here to both speakers so they match up, but this drop here also affects cone excursion. So if I remove the filter from just one of these speakers, we can see that the cone excursion starts creeping up. And what I'm going to do is I'm going to shift this graph slightly to the left to show more of the low end. So I'm going to go here into the options, and I'm going to look at this plot window, and I'm going to adjust my frequency response range to 15, and I'll raise this to 250, let's say. Now with the filter off on one of these, our tester if you will, we can see that the response here, it doesn't exceed our red line, which is considered our Xmax, which matches the parameters of that subwoofer, but that's because the box size is here, and if we increase the box size, I'm using my up arrow here inside this volume box, but if we increase this, we can actually make the subwoofer exceed the Xmax, and by doing so, we would expect that the subwoofer would have a problem achieving this because the linear travel available is exceeded. This means that the graph is not actually showing what the subwoofer would really do, and instead it might lose composure and have issues producing this, and if we keep pushing a speaker beyond its Xmax, we can expect possible damage to occur to the subwoofer. In a sealed enclosure design, volume directly impacts cone excursion as a smaller enclosure changes the Xmax potential of the design. In addition, changing the filter also changes this characteristic. So we are going to reinsert our filter. The next thing we're going to do is set our cross point on the low pass. Low pass on a subwoofer is the frequency that you want the other speakers to take over, like your mid bass. So we're going to add this as a constant to both of our designs. I'm using a 4th order 70 Hertz crossover point just for this demonstration. Now, as I mentioned, I made 2 projects, and this is so we can look at the differences live on screen. So I'm going to first set this one to a near idealized volume, and when I say idealized, I'm speaking to the QTC factor, and the ideal is 0.707. The ideal I'm using there is air quotes. It's in air quotes because there really is no such thing as ideal. It would be ideal for your circumstance. I want to point out an error that can occur, a bug in WinISD, and it's one that can get you if you're not careful, and that is creating a floating point error. I'm going to add an extra decimal point here to the end of my volume, like that, and I get this notification that I've got a can't convert floating point number. That's because I've made a totally wrong number. So getting out of this, because it's a loop, it can really mess you up. If you try to type in a new number, you get this over and over again. Quite annoying. I'm going to use my up or down arrow and see if it will correct. There it goes. It cleared out. And this lets me start over. Sometimes you have to exit a parameter and come back in and hit the up or down arrow. But what you're looking for is it to zero out so you can make a correction. And I'm just going to put in, like a cubic foot here to get back to where I want to be. The number I really wanted was 0.965, which gets us to our 0.707 QTC. Let's talk about QTC in general terms. I'm going to use very basic terms here just to make it simple for everybody to understand, but you can always go and crack open a how to design subwoofer book and see all of the details. In simple speak, a low QTC created by a larger enclosure like this creates a deeper frequency extension at the expense of a little bit of maximum SPL while also increasing the transient qualities of the subwoofer, and that means the ability for the subwoofer to, say, strike a one quick bass note like a drum hit and then come to rest so the subwoofer doesn't continue to ring afterwards. Now, this doesn't show in WinISD on any graph I've ever seen. It's something you can keep in mind with sealed enclosures is the QTC factor is more of a quality factor for the bass response on impulse hits, sharp bumps in the bass. This also applies to other frequency ranges, but we're talking subwoofers today. This QTC at 0.5 is considered to me more ideal because what I want is a more accurate sound, being a sound quality guy. But you may not have the airspace that it requires to get to this low QTC, so you have to compromise. And this gets back to what's ideal for you. So as I drop the volume, we can see we get closer and closer to where we started with this other example. Now what happens when we go the other way and we shrink the box size? It's obviously easier to put in a smaller box in a car, but what's our price we pay? The trade-off is we have less frequency response down low, slightly more volume up high, but we also have a higher QTC number. And so this gets back to the thing that WinISD does not show you directly. As you get past the 0.7 and 0.8 range and closer to 0.9, your frequency response drops off rapidly, making this less of a subwoofer and more of a mid-bass speaker. This is why you might have heard that in order to play loud low, you actually must build bigger enclosures. That's mostly true. QTC at 0.9 is going to ring more. It's going to have more of a lasting tone rather than quick, accurate sound. And again, I'm using very general terms here, but that's a not ideal thing for me on my designs. However, it's much less airspace. So you have to kind of think about these things in terms of compromise, which is kind of the name of the game when it comes to enclosure designs. Use what works. Remember that a sealed box is simple in the terms of what you're adjusting here, but there are other factors to keep in mind. Cone excursion shifts directly related to the filters you apply and the power you apply, of course, but also that enclosure size. So as the enclosure grows, the X-max, or the travel of the subwoofer is operating at a given amount of power, also grows. Your goal is to stay below your red line, so the design that you're building for the power you have and the power you intend to use doesn't exceed the limits of the subwoofer. Sealed designs only have these measures to worry about in general. There are micro adjustments to, say, things like group delay, but it's of so little consequence that it's really not worth discussing too much. You can see that the changes are very small. As we get into other alignments like ported or fourth order bandpass and beyond, this changes and you have to be much more aware and cognizant of these other things that are happening to your alignment. The complexity increases somewhat exponentially as you increase the orders of your design. One other thing to note is you might have heard about infinite baffle. You probably heard me talk about it. Infinite baffle means that this enclosure size is infinitely large. That's not true in the case of, like, say, a trunk. When you're building and walling off the subwoofers from the rest of the cabin, you won't have an infinite size. You would if you installed a subwoofer, say, and cut out the bottom of your car and then mounted the subwoofer so that the outside air was on one side and the inside of the car was the other. That would be technically infinite baffle. But practical terms, you can expect a pretty accurate way to measure this, or at least visualize it here in WinISD, by increasing the volume to a number that is really large. And the common recommendation is to take your VOS number, so 67.5 liters, which is 2.3 cubic feet-ish, and take that number and do it somewhere between, like, say, 5x and 10x. So let's try that. 2.3, it's like 15 cubic feet, something like that. In doing so, we can see that the QTC has dropped to a 0.4, which is quite low, but at the expense of some SPL, we've extended very, very far in the frequency range, even with our filters, and the cone excursion is increased, but it's still not too far. What that means in short terms is this particular subwoofer with this amount of power is actually okay in an infinite baffle alignment in general. Now, if the box was infinitely large, we can see even if I max this out to hundreds of cubic feet, the enclosure is massive or even non-existent, but this did not change much. And that's because as you get more on the extremes of these things, the frequency response is basically going to be the same. Here, let's cut this in half. Did you notice the difference? It's barely even perceptible. But as we shrink it, the changes occur faster and faster and faster. So infinite baffle, once you get to these really large numbers, you can expect this to be pretty accurate to the anticipated response. Next up, we will look at how ported enclosures work in WinISD. And we'll just leave both of these here. We'll leave one at, let's say, ideal, right? 0.707. I'm just gonna repaint these so they are somewhat out of the way. To recolor, all you have to do is simply click this little guy at the bottom here with the color and then pick one and you're set. Now, let's take this exact subwoofer and we will do it in a ported alignment instead of sealed. So this vented alignment, you'll be able to choose your alignment here. And the thing about alignments here when it comes to vented enclosures, ported enclosures, is there are more variables at play. There's the box size and there's the vent and its tuning frequency. And so this extra layer of complexity means that the alignments can be different. You could have something that has more of a boom to it, or you could have something that hits much lower in the frequency response range. So we'll explore these, but I'm just going to pick this for now, and we will call this ported. Now, right away, we're going to do a few things. We're going to set our filter like we would for the other speakers. And this is a great first step to take with any alignment that you're trying to create in WinISD, is set your filters. Make sure they match up, and you can simply click project to project and make sure that the items here in the filters stay the same. Now we'll add some power, and we'll just go ahead and put it up to the 1000 watts. And the other thing I'm going to do is make another copy of this, again just for demonstration purposes, and I'm going to retrace my steps exactly. Okay, same thing with the filters here. We will match them up, and we'll add our power in to match. So before we go too far, watch for cone excursion over limits for the alignments that you're working on at the power that you're working on. We'll leave the constant here at this setting of, I'm just going to round these numbers off to make it easier, at 1.8 cubic feet, and tuning frequency will be at, say, 23 to 24. We'll do 23. This is a very low tune, which has advantages in low frequency response, which for me, being an audio enthusiast, using a subwoofer as a true subwoofer and not as an item that plays one note very loudly, this is nice for me. This is looking very, very appealing. Let's adjust this and see what happens when we start messing with the variables that we have. So at the 1000 watts, and it will round up or down as it's doing some calculations there. So if I type in 1000 and then get away from it, come back, this may or may not change just a bit. 1.8, I'm going to leave everything else the same, but I'm going to adjust the volume of the enclosure up and down, and I want you to see how the changes affect the response. So as we downsize the box but make no differences to the rest of the enclosure, the rest of the alignment, we can see that the bass response drops, and then likewise, if we increase the box size, then the bass response increases down low. Ported boxes, the larger they are, the more extreme this shift here can be. But the cone excursion is also increasing, and we saw this just like we saw in a sealed enclosure, but it's less dramatic. And that's because at the ported frequency, the tuning frequency of the port, there is a dramatic drop in cone excursion. The ported design causes the subwoofer alignment, the enclosure and the subwoofer, to work together at the tuning frequency, and the port becomes the greatest contributor. This is determined in WinISD visually by the gain of the rear port, and we can see this gain here. And so if we change the box size, we can see that the gain changes as well. That's just adjusting the volume of the box. Now let's take this to the number that it was before with the old one, which was like 1.8, like that, and then the tuning frequency was 23, so these match. And now let's adjust just the tuning frequency. So again, just highlighting this area here, clicking on this box here, pressing up and down on my keyboard, up arrows or down arrows on my keyboard, and we can see if we make no other changes, then the bass response extends out further with a lower tune, but the overall response here, higher than the tune, drops, and that's the trade-off. With a ported box, you have these two factors to consider. The complexity increases. If you adjust both of these at the same time to get what you might say is an optimal response, so if we take, say, 2.8 cubic feet, so we'll add a cubic foot of airspace, and we reduce the tuning frequency, you can see that the frequency response is now dramatically better here in the very low frequencies. There we are. We can extend even further. And so as a sound quality enthusiast, what I'm looking for is not necessarily a flat response, but what I want to avoid is an extreme peak in the response. I can still tune out a peak in my DSP, but it's a lot easier if this is smooth, it's predictable. All right, now the problem with the ported box is the box sizes get quite large, so fitting them in a vehicle is not as easy as, say, a small sealed box might be. So you have to weigh these things out. The one thing you have to consider is the sealed box. This was one example we used for an infinite baffle, but let's take this down. 2 cubic feet, no, even less. We could. These are very space efficient. So let's say 1.5 cubic feet. Okay, so one subwoofer at 1.5 cubic feet versus a ported enclosure at 3 cubic feet. Logic says you could put 2 sealed subwoofers in the place of 1 ported, and that's correct. So if you take that and make this 2 and then make the box size double. Now the response of this to this is closer. Now let's make this red so it's easier to see. So there we go, 3 cubic feet sealed response. It's actually higher response in the 40s to 50s frequency, but then the ported takes over at about 36 and down, even with just one subwoofer. This is considering also that the whole system is taking 1,000 watts, whereas this one could technically take 2,000 watts if you had it, because there are 2 subwoofers. And so if you do that, if you double your power, a 3 decibel increase, now a sealed box outperforms a ported box of the same size all the way down to 28 hertz. And this is why a sealed box, if you have the power and the quantity of subwoofers, may be an advantage for you, because you've used the same airspace and you've just stuffed it with more subwoofers and then applied more power. Another important thing is a ported box is 3 cubic feet plus the size of the port, and that port takes space. And so if you're building an enclosure with the port inside the box, it's not 3 cubic feet, it's 3 cubic feet plus the port. We'll get into porting in just a moment. It's just one extra complexity to consider in your process here. So let's get back to some standards. We'll go put this back to 1.5 cubic feet at 1,000 watts with one driver. And we'll focus back on our ported box and get this to, say, a fair number that performs well. Let's tune up a little bit and size down the box just a bit. So about 2 cubic feet. Well, this is close to where our constant is down here, and that's fine. Okay, so let's stick with this to 2 cubic feet, tuning frequency 24 hertz. Very low tune. This is why these CSS XDX subwoofers are pretty neat. Playing this low is great for a subwoofer. So let's talk about that cone excursion. Perfectly fine, well below. Once we change the tuning frequency, you can see that this changes pretty drastically, but it's still below our safes area at maximum excursion of 28 millimeters that we saw. What about group delay? So ported boxes have a much larger group delay than a sealed box like we see down here. A ported enclosure, because the port is taking and gaining the system in SPL, that port is doing it out of phase and it takes longer down low. But this is not a problem as long as you don't have a speaker that is crossing at the same range as this, which you wouldn't. Your crossover would be like, say, 70 hertz or so. If you had this peak here over here, which you wouldn't, but if you did, this would be something you'd want to compensate for in your DSP, which would be difficult to do because it changes for the frequency. This is why sometimes ported boxes get accused of being kind of sloppy. This is one reason anyway. The other would be just a gross misalignment. So let's get this back. Yeah, it looks pretty good, somewhere around there. So group delay is a minor factor with ported boxes, potentially. What are the other things we can worry about? Well, the biggest one for a ported box, in my opinion, is excess air velocity. So there is a golden rule number that I've been using for decades now, and that number is 17 meters per second, and that would be right here on the graph. At 17 meters per second and under, the air that you hear rushing through the subwoofer vent should not be audible. Obviously, you can go a little above that and it would still be just fine in most cases, particularly so if the vent is big and if it has smooth edges, so the turbulence is less. What we do to decrease our air velocity is to increase the size of the port, and we would do this here at the vents tab, and we can adjust the round vent, or we can click this for a square vent and we can see that this changes immediately, but it's still way off the chart. You can adjust the chart size, but the reason why I have it this is that once we get past 17, we're not in that sound quality zone that I want to be in. I've also been taught when it comes to ported boxes that sound quality is going to go out the window at max power, but if you factor half power, so 500 watts in this case, half power is only 3 decibels less, and so a sound quality build will often be way less than just 3 decibels down from maximum, because music is dynamic sound. So this 500 watt number, half the maximum number, is a great starting point for realistic output of the air velocity, so you don't over or undersize your vent. Next up, we need to increase this vent, and I'm going to try a slot port. So what I'm going to do is shrink one down, so like say 2.5, and I'm going to increase this to say 10. Now right away, I've got well below my maximum of 17 meters per second. This is great, except for one major problem, and that is by going with a bigger vent, you also go with a longer vent. These are directly connected. That's how this vent is tuned. So we will kind of nudge these numbers in our favor. And what we can do is just make small changes. There we are. So a 2 by 10 inch vent on this particular subwoofer at the half power mark, which is a nice safe mark for sound quality reasons, has, in my opinion, below audible threshold vent noise that could annoy you in use. This number here is great. Now, it was pretty easy to figure this out. All we have to do is figure out how to put 47 inches worth of vent at 2 by 10 into our design. Something to think about. So if it was a round port, you could take this to a pretty big hole, and about 5 inches seems to do it. You could, fudge this around, but obviously with cylinder vents, round ports, they're hard to build on your own. You'd have to come up with, a tube of some sort, like PVC pipe, cardboard, whatever it takes. And so there's only going to be certain sizes available. And this is the inside diameter, not external outside diameter for the vent, because we're most concerned about where the air flows in and out of the vent. The other thing is that the system is making corrections for flanged ends. Always consider that you would want to have a flanged or a curved bell end on your vents where possible. This will affect their noises that they make. So let's stick with this. We have our filters, our box size, our vent, and I'm going to go back to a ported slot port just to make it more practical for daily use here. And that's what a vented box design looks like. You are wanting to watch out for over excursion. Use your maximum number for this just to prevent damage to the subwoofer in case things get to their extreme. This is well below the part where you should be concerned. With the filters in place, that makes sense. And with the right vent size, you can have a successful design implemented. Let's briefly cover the cousin to the ported box, and that is a passive radiator enclosure. The passive radiator is a device that operates like a subwoofer without the motor, so no magnet, no coil of wire. And this is a way to simulate a vent in a way without that big 47 inch by 2 inch by 10 inch slot port snaking through your enclosure, taking up precious airspace in its own. So a passive radiator, while not exactly as efficient as a ported box, is an alternative that you can kind of keep in mind. Now, I picked the CSS speaker. It turns out that they actually have passive radiators that we can use to match. A passive radiator, such as this unit right here, they are equipped with a weighted disc design usually. And so in your tuning process, you'll be able to determine how much weight you need to add to this to change the tuning frequency of this passive radiator. Also, we need these numbers to enter into WinISD to simulate the passive radiator correctly. So I'll do that now. I'm going to copy these into our notepad to make it easy to add it in. So we're going to go new project. We'll leave all the old ones in place. Same subwoofer, same driver. This time we're going to go with the passive radiator. All right, now these numbers here are going to get entered in. But again, watch the unit of measure here, and let's match these up. Also take note of this maximum moving mass. This is as much as can be allowed to the design without causing issues to the passive radiator. These parameters do not cover this, but very soon we will cover this. So keep this number in mind. Now, WinISD has a limitation of not being able to determine the correct alignment. So when we start, it's going to be probably messed up. Let's name this, and here we have it on the chart. As you change the settings in your WinISD controls, passive radiator has functions that you can change. You don't want to change the VOS and the QMS and so on, but you may want to change the mass added to the cone. The problem is, and I'll add some power here and put my filters in just so you can see this in action. We're going to match up these filters just like before. So 4th order, 70 Hertz crossover, and 20 Hertz high pass and low pass. Clicking on another project and making sure the filters match is key. Notice though that the response looks odd, to put it lightly. At 1000 watts, our little passive radiator is nothing but a peak. It's not very good for sound quality. This is where the mass added to the cone matters. So I'm just going to add 100 grams. And you see how it turns all white? So this is something that happens within WinISD that's an annoyance, if you will. All you have to do is simply get out of this one and back in to something else, and it'll refresh. The other thing is we can use the up and down arrow, and it kind of flashes, but you can still see what you're doing. It's just a bit of a light show here. It's a bit annoying, but we can work with it. There we go. So at about, let's say 300 grams, to put an even number down, we can see that we're almost getting what a ported box could do, but not quite. Still, it's not too bad, and we don't have a big port to deal with too. We just have to spend the extra money for a passive radiator. Or maybe we don't want just one passive radiator, maybe we'd want more than one. So we can actually change the number here and change the behavior again. And with 2 passive radiators, we're actually very, very close to a ported enclosure design. So 1 powered subwoofer and 2 passive radiators, almost, but not quite, equals the overall response you would expect from a vented enclosure. However, let's get perfectly matched here on the volume. There we are. Now here's the other thing. That other vented design had space taken up to match the vent, but it's not part of this original number that's provided. You know, this 2 cubic feet or 1.8 cubic feet, whatever we pick, that number does not include the vent inside. So in a passive radiator design, if we had the space to spare, we could extend to a larger box size and our frequency response would change again. It's a matter of compromise, like all alignments are, with the added variable of adding mass to the cone. And as we saw, we were allowed to put up to 1200 grams per cone per passive radiator, which allows a very deep response. Not particularly great for our design we're looking for today, but it may work in other alignments. For instance, if this box were to get small, very small, 2 passive radiators plus the sub in a teeny tiny box actually has a pretty decent response frequency wise. It's better than a sealed box. These are the advantages of passive radiators. Obviously they come with disadvantages to match. So I'm going to put this back to what I would consider to be a nice easy alignment, just something about like that. Now we have 2 passive radiators in this design. Let's go in here and look at our cone excursion. So it's well within reason for the cone excursion, and this is the primary speaker subwoofer cone excursion. What about the cone excursion of the passive radiator? It's well below limits. If we go to 1 passive radiator, it's not. This is exceeding our limits by a rather dramatic amount, off the chart. Changing the mass of the cone drastically changes this, but there we are, let's say 900 grams. We'll have to make sure, very, very sure, that we filter out anything below these really low frequencies. It should, because your music should never go this low, but what we might have to do is increase our strength of our crossover at our high pass to protect our passive radiator so it doesn't rip at a very low frequency. Also, the response is shifted. It's not quite as punchy with 1 passive radiator. So in this particular design, the optimal, and that was in air quotes, the optimal design that we can see, at least in this build, is something closer to a 2 passive radiator design with about 600 grams of added mass per cone. And so that's how passive radiators work. You can use them almost like a vented enclosure, but it might take more than 1 passive radiator to achieve your goals. And certainly adding mass is one of those extra variables to consider. Also, just like ported boxes, that passive radiator is operating in a slight delay to the rest of the system. So passive radiators encounter the same change in parameters, the same delay factor as a ported enclosure. Okay, we'll leave these in place. Maybe it's time to talk about Isobaric just a little bit, just briefly. So Isobaric means that I would be installing 2 subwoofers opposing each other, and I'll just use that as an example. We'll do a closed design with, call this clamshell design, same filters and everything in place, and same 1000 watts. Now the important thing here is that you're applying 1000 watts across 2 subwoofers, but they're sharing the output, and that means the bass response, the overall SPL, is going to be a lot less than a regular sealed box, at the advantage of half airspace required. So in a condition where airspace is an absolute premium and you have none to spare, but you can handle applying extra power to your system, clamshell designs are an option. This is why they were very popular in the early days of car audio in the 80s and 90s. When I saw them frequently, I saw them in designs where a big 15-inch subwoofer, for instance, had no business being inside such a small box. And that's because it had another big 15 clamshelled with it. So one was inside the box and one was outside the box, connected together with a ton of power. And what it would do is make the box requirement half to get the response plot the same, minus the SPL change. So for instance, if we take this to 2000 watts, 2 subwoofers, we get closer. This should be a 3 decibel difference. So say at about here, we're at about 107. We expect this other one to be 110, 109.8 something. So it is. And so that 3 decibel change, while it is there, it's not too noticeable, but you have to have tons of power. But again, your box size is absolutely micro. So clamshell, definitely an option, but not a very popular option these days because a lot of subwoofers don't require massive airspace to start. I'm going to go ahead and close this. And we're going to start with a 4th order bandpass enclosure for our subwoofer. Bandpass adds yet another level of complexity to the design. So we'll use one driver, bandpass, 4th order bandpass, means that the subwoofer is in a sealed box on one side, venting out its output entirely through the other side, the chamber. Alignments can vary in a 4th order box. We'll just start with this here. So this will be bandpass. And again, we're just going to set our filters in place. We have our filters matching and we'll apply power. Okay, right away, this is not a bad response. Keep in mind our ported boxes are up here. Ported and passive radiator are up there at the top. I'm going to recolor this. Okay, now I've got a rear chamber where the subwoofer is enclosed, the sealed box portion with one variable. That's the volume of this enclosure. I have a front chamber with the volume of this area and a tuning frequency. So now I have 3 variables to contend with to achieve a response plot that I like. Right away, there's no advantage here in the design. I've got, let's just round up some numbers to make it a little easier. Say 1 and 0.5 cubic feet and a tuning frequency of say 40. There's no advantage of this over a ported box, also at 1.5 cubic feet. Now those boxes were actually like 1.8 and 2 cubic feet. So if we distribute some of that space, we can see as we increase this here on the rear chamber, it actually lowers our performance. So changing to a smaller airspace increases this little hump, but still gets nowhere near a ported box for this particular subwoofer. If we change the front chamber, we immediately can see making a bigger front chamber where the tuning port is, this makes this whole response rise beyond the ported box, but only at a certain frequency range. So as an example, let's push this to an extreme. From 53 Hertz all the way down to 30 Hertz, this bandpass box has a rising and then falling response centered at the tuning frequency of 40 Hertz. This isn't very good for sound quality, although you could tune it out with EQ, but you can use this to your advantage in a bandpass box by optimizing the response. The trick is to figure out that sweet spot, making one small change at a time to figure out what you can give up and what you have to stick with. But a bandpass box typically will not sound as clean as a ported box, even if you get the responses pretty close to each other, and I'll show you why. I'm tooling around looking for that sweet spot with this design, not finding it too easily, but maybe something like this just to get rolling. So let's shore up these numbers so they're simpler. Okay, so I'm just going to stop there with this design. Let's talk about what else we have to contend with. You'll see here in the cone excursion area that it has a similar, but not quite exactly the same type of curve or dip in cone excursion that we saw in the ported box. Just want to make sure that this number here never exceeds that X max, just like before. Changing the volume subtly changes this capability of excursion on the front chamber, but on the rear chamber, it changes this curve here. Also, changing the tuning frequency changes things as well. I'm going to restore this back, something like that. So cone excursion. Now you don't have a rear port to contend with, but you do have a front port to contend with. And this is of course way off the charts. Now bandpass, because it is tuned to a frequency that's higher than that ported design, we want to make very sure that we set this well below that magical 17 meters per second target. So what I'm going to do is go with the slot port again, and this time try something a little bigger. And I need to adjust the power output by half again to make things reasonable. There we go. What we could expect is a vent similar to that of our ported enclosure. What I have here is like 2 and 125, so that's 2 1/8 by 10 with 38-inch vent, and this would come into this area here. So this would need to be like 1.25 cubic feet plus the vent to equal the front chamber. And then we would expect also the group delay to have a rising response similar to our ported enclosure. It's not actually as bad as a ported enclosure in this configuration. And if we change this, we can see that it rises dramatically potentially, but it does depend on all the rest of your alignment factors. Changing anything changes the overall group delay, cone excursion, air velocity, gain, everything. This particular subwoofer, we can tell it's not optimized to bandpass, but there are certain subwoofers that absolutely are, especially ones with ones that were also really good with closed boxes and sealed boxes. If it's very good with the sealed box, it might also be very good with the bandpass box. There are other factors to consider with bandpass besides group delay and the frequency response, but in general, if we keep it to those basics, you should be fine in designing the one you want, especially if you have DSP, digital signal processing, to compensate for, say, peaks or valleys that result in a bandpass design. Next up, let's take a look at 6th order bandpass. This is where the complexity ramps up so dramatically that WinISD can't help us, but we can figure it out for ourselves if we take the time. 6th order bandpass has a rear vent and a front vent. The subwoofer's in the middle. No alignments available. Again, doesn't scare me. Here we go. Expect these boxes to be kind of large, not just for the vents, but for the enclosure itself. First, as always, we add our filters, high pass and low pass. Next up, we'll add our power. We'll start at 1000 watts. We're seeing a pretty wild curve here in the SPL. And we have now an extra variable. We have the volume on the rear chamber, the one with the subwoofer inside. We have the tuning frequency, and we also have the front chamber and its tuning frequency. And they can be set to the same frequency, but they cancel each other out. So in a 6th order design, you want to build in a way that you get a response that gets better than your ported box might be, because again, the ported box is simpler than a 6th order, but gives you the advantages you're looking for in such a complex design. What does this give us? This gives us more mid-bass, less very low frequency extension. Let's see if we can optimize. By adding airspace, we can get much closer to that of a ported enclosure, but we have a stronger mid-bass. Now the thing is about this combination, I don't really need this. What I need to do is shift all of this to the left if possible. So is that possible? Let's try adjusting tuning frequency. It's not really getting us anywhere. Let's see if we can go to Okay, now we're talking. Let's try. Okay, I'm going to stop here and just take a look at what we've done. What we've managed to do is create a box that is quite large. Let's go with some numbers that are slightly less extreme, still pretty high. Let's use this 3 cubic feet on this side, and it's very sensitive to the changes you make. Earlier I mentioned that the higher order you are, the more critical it is of error. And what I mean by error is, let's say you make a box that's, slightly different box size dimensions or different volume, or maybe you forgot that the subwoofer itself consumes airspace. That's all known as displacement of the subwoofer. Making these changes, small as they are, tiny changes, makes a big difference to the response, potentially. But let's stick with something like this. This is good. It's numbers we can agree with here. Okay, so in this response, below 28 Hertz, which is quite low, but below 28 all the way down to the end of the response, the 6th order bandpass rules in output for the 1000 watts of power that it has. Otherwise, it really is not at an advantage over the other designs. But every speaker is different, and there may be an instance when 6th order is the right answer. A problem with going up in order, and thus the complexities and thus the error issues that come up, the stacking error issue, is that these parameters that the manufacturer provides, these parameters are not always solid. As the speaker heats up in use, or breaks in, or wears over time, or through manufacturing variations in design, as one speaker is built and another speaker is built, these numbers can shift 5 to 10 to 15% or more. By shifting like that, an enclosure of higher orders, 6th order being more so than 4th order, more so than 2nd order, ported and sealed. This means that your tuning could drastically be different than what your predicted response is. Do keep that in mind when it comes to higher order boxes, is it might be not what you modeled, because the specs might be just different enough to start screwing things up. What I recommend with a 6th order box, and maybe to a 4th order box, is consider investing in a speaker analyzer that can measure the exact numbers, which you could then put in this chart. You could have more accurate measurements than what the manufacturer provides, given their range of acceptable parameter drift. All right, back to it. 6th order, SPL's looking pretty good. How about cone excursions? Well within reason. How about group delay? Okay, so as we get our middle mid-bass range here, we can see that we're gaining some millisecond delay, and that may be something we need to think about when it comes to doing our DSP. And then our sixth order at the lower range, it has a pretty significant delay, and this means that we can expect a slight bit of, I don't want to say it's going to sound bad, but it might sound slightly smeared or sloppy, to use a phrase that's used too much, when it comes to a sixth order design. The other thing is, it is relatively efficient on power, but it used huge amount of airspace. If you took this same 3 cubic feet of airspace or so, plus the vent sizes that you have to accommodate, which we haven't even finished yet, then you may end up with a box that works better as, say, 2 subwoofers in the same space in a vented alignment. So sixth order may not be the right answer when you have plenty of power and plenty of subs to put in the same space. But let's try to optimize the sixth order air velocities. Let's get them under control. We're going to follow our rule here that we've created of half power, and I'm going to work on this slot port design as before. I'm going to turn these both into square or rectangle. I'm going to affect in my rear port air velocity chart just the rear chamber here, but I wanted these to kind of line up. So 2x10 is below the 17 meters per second range that I consider to be the sacred safety range. So let's stick with that. And the front chamber is governed here by the front port air velocity chart. And we can change this to say maybe a 1 3/4 vent. And so this vent would be 45, almost 46 inch or so vent length. And this one would be 32. And then keep in mind that that would be to achieve this response with this maximum output. And there you have it. You were able to see how a sixth order, a fourth order, passive radiator, ported, and sealed enclosure would all stand up with different options as we went with the same subwoofer. So what happens when you want to compare one subwoofer to another? So let's see what happens when we want to compare for a known amount of volume that we want to work with, what subwoofer might work best for us. For instance, we'll just keep it simple with a sealed enclosure. So I'm going to go ahead and remove all of this and go find a subwoofer I'd like to model besides the one we just beat up here all this time. There's one I had on my mind, and this company called Prodigy is really appealing to me for the prices and the performance that I see in the specs. Now, I haven't heard them, so I'm just going by specifications, which is not a fair assessment, but it is one I'll use today. So I see that they have these specifications. I don't see LE, the coil inductance. That is unfortunate. I wish they showed it. However, it is enough for us to model. I'm going to pick this one right here, new Prodigy Audio, and we'll pick this 15-inch. If you can fit them, I really like 15-inch subwoofers in sealed boxes. All right. And then I will take some of these data points here as my comments. Okay, we're going to drop these numbers in just like always. Same process as before, no different, except I don't have LE and I don't have frequency of LE. I do have X max. And I think I saw X max and X mechanical. So I see a 40 millimeter X mech before things start happening in a bad way. And remember, if you see something that reports X max but says peak to peak, just divide by 2 to get your peak. So you want to pick your X max, your X lim, and this one's product power 1200 watts. I could have sworn I've seen these guys run harder than that. Interesting sub point. I found that this subwoofer at Sound Solutions Audio is not 1200 watts, but rated at 1500 watts. Take it for what you will. It probably could handle it, but I am going to, for now, stick with the product website as my guide. I am going to put in my comments though. SSA website shows 1500 watts RMS. Okay, we are going to put the 1200 in and save. Now we're going to plot it out in a sealed enclosure, I think, just to keep things simple for today. Adding our filters as always. Here's our SPL at a box size of 2.3 cubic feet. Shrinking this down doesn't change the response too much. I'm just going to go with 2 cubic feet just to keep things even. Cone excursion, not even remotely close to maximum. Even if we change the box size to something closer to infinite baffle, there's no chance of exceeding here. So these might be very good for infinite baffle use. Always nice to see. Now, what's a competitor to this? Right away, I was thinking this could be pretty close to a stereo integrity SQL 15. So let's pick that out and see the differences, if any. Again, apples to apples here. All right, same thing with the filters. Everything needs to match here so we have a fair assessment available to us. What does an SQL15 do for power? I think it's 1000 watts. I've seen people push it way harder than that, but for now, I'll leave it at 1000 watts. There we are. What's the box size? 2. I'm going to go ahead and just match them up. Okay, so let's recolor one just so it's separated from the other. Very good. So Prodigy in blue, SI in red. We can see that up till about 50 hertz or so, there's absolutely no difference in response that you could audibly detect. And then below that, it's debatable if you'd have an audible change there between the two subs. So for these two, assuming nothing else other than just what we can see on plots, the group delay, SPL, all of it's about the same. This cone excursion is slightly less for the Prodigy, but it's still all below the max. Now, the thing is, the Prodigy is running more power, but not too much more. It's 200 watts more. It's not nothing. If we gave both speakers the same power, say we were limited by our amplifier, now we can see that there is a subtle advantage with the stereo integrity. It is slightly more efficient. Is it audible? So at about 40 hertz, we're at 112.7 for the stereo integrity versus about 111. So a decibel and a half. Not truly too audible, but it is there. It does exist. What does this mean? This means that for this alignment, this build, the QTC of the Prodigy is at 0.728. Stereo integrity is 0.737. I'd argue you probably could not hear the difference between these two subwoofers at these specs. What happens if we try to optimize these a little bit? What happens if we give this a bigger box, say 4 cubic feet, and then we give the Prodigy a 4 cubic feet? Same expectations here. The stereo integrity is slightly more capable at low frequencies with the same amount of power. The stereo integrity could take more power, but it's not rated for it. The Prodigy is rated for it between 1200 and 1500 watts, depending on who you believe. There's 1200 and there's 1500. So it's trading blows with the stereo integrity, depending on how much power you provide it. These are good results. Let's try adding in another subwoofer so we'll have a three-way comparison between them. I was looking at a Ground Zero, even just their base model subwoofer was on my mind. And it does favor a closed or bandpass design, so we'll call this Ground Zero 15 sealed. Add our filters as always. Apply power. The Ground Zero supports a 1000 watt RMS, and the box size at once is pretty big, but let's take it back down to 2. So at 2 cubic feet, we are at QTC 8.42. It's still acceptable to me. It's not getting into that ringing zone. Let's take these all back down to 2 cubic feet. Here we are. So now we have, again, they all seem to match up almost exactly. The Ground Zero, I need to recolor. Here we are. So the Ground Zero sub for the enclosure that it's in requires slightly more excursion, but well below its maximum of 25 millimeter, and the SI and the Prodigy, all with a response that is virtually identical. Again, the Prodigy is running more power, so if you had a limitation in power, the Prodigy would not be as great a choice. If you had a surplus of power, that may be different. And so that's just a simple sealed box comparison and a way to use WinISD for that kind of comparison. How about a mid-bass shootout? So here's something I found that WinISD can do for you nicely with mid-bass speakers, and that is figure out whether or not they're very good at handling indoor infinite baffle designs, or if they're not suitable for that. Because what we see in the car audio industry is a fair amount of speakers that aren't really made to go inside a car door, and the result is low bass response when you expect it to have something that was very good in bass response for the speaker size. So I thought I'd just take a moment and show you what this looks like for WinISD. We'll shrink down to just one subwoofer, and we'll keep this Ground Zero. It's a good price, good value. And now we're going to extend out our plot window to be more of a mid-bass friendly graph, and this will be by adjusting the frequency response closer to, like, say 750, and that way we can get down in this mid-bass range. Now I'm going to add a mid-bass to the project. I'm going to add a One Audio MB8E. That's a 8-inch mid-bass driver. It wants a vented box, but that's not how car doors work. They work like infinite baffle mostly. So we're going to add our filters, and this time our filters are going to be a little different. Our high pass will be everything that we pass beyond, and that's actually our crossover. So our fourth order 70 hertz crossover, and then the other side of this is our low pass, which will say fourth order, let's say 300 hertz. There's our mid-bass curve. Let's give this 100 watts. It could take more, but this will be a nice little comparison. So they're very efficient, so we can see right away that that's the case. But we're in a box size that's not realistic to car doors. Car doors are leaky infinite baffle. Leaky in the sense that the front wave and the back wave are going to intersect at some point due to the natural holes and leaks in the car door. It's not airtight. So we're just going to make this draw out to closer to about 5 cubic feet. This drops our QTC to 0.5, which actually should be ideal because our cone excursion is about 6 millimeters on this driver, and it is absolutely nowhere near that. And even if we push it, see here I am at 150 watts or so, and I'm still nowhere near the limit. So we'll go back to 100. It's a good woofer. I'm going to add an 8-inch from another brand, and so we can compare them more directly. I'm going to add one from a website, and we'll go find one that works. I picked out a Silver Flute 4-ohm woofer, and whatever happens, happens. We'll just look and see what the results are. Maybe it's going to be a good choice. It's a good value. Only costs 52 bucks each. What we're going to do is pull our specs and get them in our notepad. We got them, and we're going to add the woofer into our driver editor as a new woofer. Let's see the difference between a Silver Flute and a One Audio. And again, you'll want to make sure that you set your filters right away. High pass of 70 Hertz, low pass 300 Hertz. Linkwitz Riley 4th order. This should match the same. It does. Next up, we'll give it the 100 watts of power, and we need to match the box size. Again, gonna use the same here as our OA mid-bass. There we go. So we can see, coloring it differently just to make it a little easier, the Silver Flute cannot play as loud as the One Audio mid-bass at the given 100 watts, everything else the same. And the SPL matches the cone excursion. We expect the OA to have more cone excursion because it is more efficient and therefore it's moving around more for that 100 watts of power. If we take the One Audio mid-bass down in power to match the SPL, we can get an impression of how much more efficient it is. And it has almost the exact same response. Bet you it's about half. Yep. So it takes half the power from the One Audio mid-bass to equal the Silver Flutes in output. Everything else is equal as we can get it. And that's how you can use this to compare. Okay, there's just some examples of using WinISD for comparison reasons. You can help find issues before you even cut the wood, break open your car door, whatever you've got to do. You can model it out and see where things are likely to go. Couple things to keep in mind in closing. This response we're looking at on screen for, say, this subwoofer, it's not actually going to be what you hear in the car, and that's because cars themselves have a cabin gain, a frequency dependent gain that applies to the fact that it is a cabin space, an airspace of its own. This is something you don't see in, say, a large home theater room. You would see flat response there if everything else is equal. But in a car, there is a inherent bass boost at about 40 to 45 Hertz. So this is something you won't see in your WinISD response. You could simulate it with a filter, but in my opinion, it's best just to kind of consider that something that all of these have, and you can tune around it anyway in your DSP. It's only a gain, not a performance drop, so you can tune out, and if anything, it just saves you a little bit of power on the low end, which is great. All right, with that, I'm going to wrap up for now. It's probably long enough video as it is. Thank you for joining me on the Audio Foundry. I do hope you got something out of this WinISD basic tutorial. There are a lot of things about WinISD I have skipped on purpose to keep it as simple as possible, and you may have other ways of using WinISD, and feel free to share those in the comments. It's how we all learn. This was just there to get people started with this program. It's aging, but it is still quite useful in many respects, and it is easy to use once the basics are understood. All right, thanks so much for joining. Take care.